Okay, we have, in this one we got y, where we have a fourth order derivative plus third order derivative of y minus 3 times a second, and so on. And we have is equal to 0. And if we take what we have and translate in terms of characteristic root notation, okay, so as an algebraic expression, we have r to the fourth plus r cubed minus 3r squared minus 5r. And since the last term in y is not a derivative, again, this translates to a constant with minus 2. And with Descartes' rule of signs, okay, I'm considering not only the general input r, but also the opposite sign input where we have negative r. Okay, so taking this function and hypothetically having negative r as the input. Now with the even roots, like in the case of the fourth degree of negative, that is going to be a positive. And we have negative r cubed is going to be minus r cubed minus 3 times the square of negative r is still going to be negative 3 times the square of r. So we have minus 3r squared. Minus 5 times negative r is going to be a plus 5r. And again, we have minus 2 to follow. And now we have for f of r, if we count up the number of sign changes going from one term to the next, okay, so we have, so we got a positive to a positive. Now we got a positive to a negative. So that is one sign change. And guess what? We have a negative to a negative, and then a negative to a negative, so there is no more of a sign change. And for f of negative r, okay, so we have going from r to the fourth to minus r cubed. We got one sign change. Negative to a negative, not a sign change, but now from a negative to a positive, we have a second sign change. And then we have going from a positive to a negative, there is a third sign change. All right. Now we got a fourth order equation. And looking at what we have for the roots, okay, so we can say we have like hypothetically. Okay, so you have like your positive, negative, complex roots, and you're going to have the total to be at 4. And for what we have in the layout, okay, so we have for the positive, okay, so you have one sign change. And that's going to be locked in, so we are going to have a positive real root. Now for the negative, we have 3 sign changes. And we have 1 plus 3 is going to be 4. So in this hypothetical case, there will be no complex roots. But if we don't have 3 of the negative, now the for what we have, if we have anything other than the number of sign changes, you're going to have a decrease by an even amount. And so I cannot decrease from 1 to go to negative 1 because I have to have, integer amounts that will add up to 4. That is natural number amounts. Okay, so we have positive 1. Now, if I have anything other than 3 negative roots, this is going to be a drop by an even amount. So if I don't have 3 negative roots, I'm going to have at least 1 negative root. And anything that I have given up for the negative roots will be transferred over to the number of complex roots. So I have 1 plus 1 plus 2, and that is going to come out to 4. And so for what I have in this particular case, all right, so I have this possibility. Okay, I'm going to have 1 positive real root and up to 3 negative real roots. But on the other hand, it could be 1 negative and 2 that are complex. And for what we have in the case of our given function, again, so just going back to f of r, and without writing all the terms out, so I'm just interested in just the first and the last coefficients. So you have like 1r to the fourth and minus 2, okay, and you're going to have a setup, okay, where we have for the leading coefficient, we'll call this p. Say that we have p is equal to 1, and q, last coefficient, that is going to be negative 2. Okay. And for what we have in terms of the integer roots of p, okay, we have 1, and so only integer roots would be positive and negative 1. And for what we have in terms of the integer roots of q, with q at negative 2, and the only integer roots, okay, so we have plus or minus 1, and plus or minus 2. Now for the rational roots, that might work into the polynomial function case. You have for your rational roots, this will be for what we have in the case of q over p. So you have like q over p, so it could be positive negative 1 and positive or negative 2. And just running through what we have in the case of our given function f of r. Okay, so you have f of r. Okay, and if I were to test out like 1, negative 1, 2, negative 2 to see what is going to set this equation or this function equal to 0. Okay, so if I have like 1, you got 1 plus 1 is 2, and you got minus 3, so we're on the wrong trajectory. If I go with negative 1, where we got 1, negative 1, and then we have, see, that's 0. 0 minus 3 is negative 3, and then we have plus 5. Okay, so that's going to be plus 2 minus 2. Okay, so one root is going to be negative 1. And then we have with, so if I were to test out 2, we got 16. And then we have plus 8 is 24. And then we have minus, what's going to be 12? So we got 12 minus 5 times 2. And then we have minus 2. And it's going to turn out that in the layout, okay, we're going to have a couple of roots. Okay, so I have r is equal to negative 1 and I have r is equal to 2. Now, again, okay, so we have this possibility, and what I mean by this is that now it doesn't mean that, okay, like the 3, this could be repetition of the same root. Okay, so the negative roots don't necessarily have to mean that we had 3 distinct negative roots. It could be like the same root but repeating twice over. And looking at what we have for this particular function, like taking the zeros, say if I have, like with the use of synthetic division, so if I have like negative 1, I have like 1, 1, negative 3, negative 5, and negative 2. And we have applying the process. Okay, so bring down 1. Negative 1 times 1 is negative 1. 1 minus 1 is 0. Negative 1 times 0 is 0. Negative 3 plus 0 is negative 3. Negative 1 times negative 3 is positive 3. Negative 5 plus 3 is negative 2. Negative 1 times negative 2 is positive 2. And we have the last column total to be 0. And if I go through the next round of synthetic division, and say if I draw out the number 2. So for what I have in this go round, with the synthetic division again, so bring down 1, 2 times 1 is 2, 0 plus 2 is 2, 2 times 2 is 4, negative 3 plus 4 is 1, 2 times 1 is 2, negative 2 plus 2 is 0. Okay. So you have complete divisibility. Now going back to what we have in our expression. Okay, so this leading one is in reference to r to the fourth. And again, for the quotient carried over, we have r to the third. And if you notice, with the 1, 2, and 1 brought down, we have r squared plus 2r plus 1. So looking at taking what we have for f of r. Okay, so you have -1 as a root, 2 is another. So from r at -1, okay, we have the binomial r plus 1. From 2, I have r minus 2. And we have with the quotient, we have r squared plus 2r plus 1. And if I set this to 0, and notice r squared plus 2r plus 1 is a squared trinomial. And notice I already have r plus 1 in play. So we have in the characteristic root equation terms r plus 1 times the square of r plus 1. We have the cube of r plus 1 times the quantity of r minus 2 is equal to 0. And guess what? We're going to have -1 is going to be a repeating root, and it's going to repeat twice. So you're going to say, in essence, because they have repetition, we have R1, R2, R3 to be the same. And for the second distinct root, but just drawing out as the fourth, we have R4 is equal to 2. And so we're going to have for y of x, okay, we're going to have c sub 1 times e to the -1x. And we have plus c sub 2, and signifying the repetition of -1, we have c sub 2x times e to the -x. And signifying the second repetition, we have c sub 3 times x squared times e to the -x. And then we have plus c sub 4 times e raised to the 2x. And that is going to be the general solution for that particular equation.